So what we want to add now is the idea of how we determine the pressure within a fluid. What does that mean? And then we'll also talk about how we can talk about the pressure at different depths within some fluid. So let's take our container over here on the left that's containing some fluid. And so if we put a surface into that, this surface has some area, and the pressure on that surface is going to be determined by basically the forces that push back and forth on it. And so we can think about that pressure, the way it relates to those forces is that the pressure P is going to be equal to the perpendicular component of that force divided by the area of the surface. And so the force per area is giving us some sense of what the pressure is. Now, the couple of critical things to recognize about this equation, that even though we clearly talked about forces as vectors and we talked about the area as a vector, pressure's defined to be a scalar. So it is a scalar quantity. The other thing we want to understand about pressure, of course, is its units. And if we think about the units of force divided by units of area, that's newtons per meter squared in SI. And that has its own name, that's PA for pascals. So the units that we're going to use for pressure is going to be the pascal. Now, the pressure value that we're most accustomed to hearing about is atmospheric pressure. And of course, atmospheric pressure is defined in terms of an alternative unit of pressure, is it's just 1 atmosphere. 1 atmosphere happens to be 1.013 times 10 to the 5th pascals. So this is a little over 100,000 pascals. It's the same thing as 1 atmosphere. So atmospheric pressure is this value in pascals. It also happens to be 14.7 psi. It also happens to be 1.13 or 1.013 bar. Or it's 760 torricellis, which is another way of saying 760 millimeters of mercury. So all those are possible units for pressure. You'll run across some of these various units in different situations. And again, we're going to focus on using pascals. And so the thing to keep in mind is that the equations we're going to work with, plugging in 1 atmosphere will often get you the wrong answer. Because instead of plugging in a number that's basically 100,000, you're going to be plugging in something that is significantly smaller. So just keep in mind that this is the value that we want to use when we're doing pressure calculations in SI. So where does this atmospheric pressure come from? Well, based on what we've just talked about, we can think about some surface sitting here on the surface of our fluid. And so since this surface is in contact with the air, and the air is at atmospheric pressure, then basically the surface here has to be at atmospheric pressure, which means that there has to be some force due to atmospheric pressure that's pushing downward on the surface, on that little chunk of area on the surface of our fluid. So this begs the question, well, what is it that's generating this force due to atmospheric pressure? And so the way that we want to think about this is sort of, well, let's blow up that surface, and if we think microscopically, we know that the atmosphere has a bunch of air particles. Those air particles are running around, and basically they're randomly oriented. Some are moving faster than others, some are moving slower, some are moving up, some are moving down, some are moving in, some are moving out. But there is a small subset of those particles in the space sitting above a little area within the surface. There's some subset of those particles that are bouncing off the surface of that fluid. And as they bounce off the surface of that fluid, that obviously generates an impulse on those particles to get them to bounce off. That impulse is related to the force that the surface has to generate on the particle to get it to bounce back. That force from Newton's third law has to be related to the force that the particles are exerting on the surface as they bounce off. So this force that's being generated by atmospheric pressure comes from the particles as they bounce back off that surface. So if we want to take that surface and now think about what goes on at depths lower than the surface. So here again was our little chunk of area, and all we've done now is said, well, let's let this little chunk of area be the top of some little box. And so it's got the same area on top and bottom, and now our box has some little height h. Again, we know that there's this atmospheric force sitting on that's acting on the top surface of this box. And of course, because this box is filled with a fluid, it's going to have both a gravitational force that's pulling down due to the mass of the fluid that's inside our box, plus there's going to be a second force that's pushing up from the particles within the fluid that are bouncing off this bottom surface. So in the same way that our air particles are bouncing off the top surface, we're going to have particles of our fluid that are bouncing off the bottom surface, generating this force that points up. And so we can think about these three forces, the two of them that are due to these pressures on the top and bottom surfaces, and then the weight of the fluid sitting inside this box. And for a fluid that's not flowing, right, then we end up having a static equilibrium problem. And so this tells me that there's not going to be any acceleration, so all these forces have to add up to be zero, which means the force pointing up has got to be balanced out by the two forces that are pulling down. So that's the force from the pressure on the bottom has got to be equal to the force from the pressure on the top, atmospheric pressure, plus the weight of the fluid. Well, I know that the density is nothing more than mass divided by volume. So if I take my density equation and solve it for mass, I get that the mass is density times volume, and that's often an easier thing to do with fluids, is to measure their density and the volume they take up rather than trying to measure their mass. So we're going to substitute that in, and so we get this expression now. And then in terms of thinking about this volume, well, this volume, again, it's nothing more than the volume of this box. This box has an area of A on the top and bottom surfaces and a height of h. So this area times this height will be what the volume is. And so when I plug that in and then divide my entire equation by the area, what I notice is now I've got three terms. The first one is this force over area. That's the pressure at the bottom surface. The second term is the force due to the atmospheric pressure over area, so that's my atmospheric pressure term. And then the A's cancel out in this last term, and I'm left with rho GH. So this equation tells me what the pressure is at a depth h below the surface, assuming that the surface is at atmospheric pressure. And we can generalize this. And in generalizing it, it says, look, whatever your two pressures are, and so this could be, hey, we could start at the surface where it's not at atmospheric pressure, we could start at the surface where it is at atmospheric pressure, we could start at any 2 points within the fluid, it doesn't matter. So just in a more general sense, the pressure at some lower point that we're calling P2 is equal to the pressure at some higher point P1 plus this rho GH term. Again, rho GH only cares about the density of the fluid, gravitational acceleration, so 9.8 meters per second squared, and then how much farther down you go, so the distance that point 2 sits below point 1. So we can use this to calculate the pressure at any depth within the fluid, knowing the pressure at some other